Hello everyone, I am Dr. Alok Agrawal, working as an Associate Professor in the Department of Mechanical Engineering, Sagar Institute of Research and Technology, Bhopal. So in this video, we will be discussing on subject turbo machinery having subject code ME603. The topic of this video is various heads in water turbine and the efficiencies of water turbine. So let us start with our topic. So what we will see that in water turbine, we have to deal with two types of head, that is gross head and net head. Let us understand what is gross head. But before going into the gross head, we have to know what is head raise and what is tail raise. See, what is happening here in water turbine, what we are doing, we are storing the water in dam, and from that dam, with the help of pen stroke, we are taking that water and striking that stream of water into the turbine blades. So that turbine will rotate and generated mechanical energy, which this mechanical energy is later converted into the electrical energy. So this is the overall working of turbine, water turbine. So the level at which the water is stored in the dam, up to which the water is stored in the dam from the tail race is called headrace. The distance between the tail race and headrace is called gross head, and the water stored in the dam is called headrace. The level of water in the dam is called headrace, and after striking the blade, the water is discharging somewhere and it is getting stored somewhere. Where it is stored after striking, after transferring its kinetic energy into mechanical work, it is getting stored in some place, and that place, the level of water is known as tail race. So there is head race from where the water is coming, and there is tail race where the water is getting stored after striking the blade of the turbine. So what is happening here? There is a two races, head race and tail race, and the distance between this two race is called gross head. Okay, so the difference between head race level and tail race level when no water is flowing. Again, see, when no water is flowing, because when the water flows, there are chances that the level of head race may decrease or the level of tail race may increase. So we will not get a constant value. So when the water is not flowing, the difference between the head rest level and the tail rest level is called gross. But when this water flows, there is a loss of energy. There is a loss of energy. So the effective head available at the entry of the turbine or the entry of the turbine blade is not same as that of gross head. So after removing the frictional losses which is causing during the flow of water in this pen stroke, we can get net head. So it is also called effective head, and it is defined as the difference between the gross head and the loss of head due to friction. So it is H is equal to Hg minus Hf, where Hg is gross head, H is net head, and Hf is loss of head due to friction. And this HF formula is 4FLV square by D into 2G, which we have already studied in fluid mechanics subject. So this F is friction factor, L is length of pipe, V is the velocity of water in this pipe, D is the diameter of pipe, and G is gravitational acceleration. So once we know all the value, we can easily evaluate what will be the loss of head due to friction. So these are the two heads, gross head and net head. Next, coming to the efficiencies of the turbine. So first of all, hydraulic efficiency. So what is hydraulic efficiency? It is the ratio of power given by water to the runner of the turbine. See, whatever amount of water energy which is given to the turbine runner to the power supplied by the water at the inlet of the turbine. Means how much water power is there. So if we'll see in simple words, so it is the ratio of runner power to the water means water power means how much power water is having, and runner power means how much out of that how much power the power is transmitted to the runner and runner will start rotating. What is runner? Runner is the cylindrical component or the circular component over which the blades are mounted. So if we'll say mathematically is runner power divided by water power. This is hydraulic efficiency. So what is water power? Water power depends upon the weight of the water which is striking on the blade. So it is W into H, that is W, capital W is weight, which can be further written as rho into G into Q multiplied by H. H is net head. Here we are not taking gross head, we are taking net head because this is the effective head. So this is water power, which is denominator, and runner power, it depends upon the type of turbine. If we are talking about Pelton turbine or Pelton wheel, the runner power will be W, again weight, by G. VW1 is the velocity of whirl at inlet and velocity of whirl at outlet, VW2, multiplied by U, that is the tangential velocity of the blade. Here in Pelton wheel, the tangential velocity of the blade is constant at inlet and outlet, but in case of Francis turbine, this varies. So we have to take here U1 and U2. So this is the formula of runner power for Pelton turbine and Francis turbine. So hydraulic efficiency is the ratio of runner power by water power. And this water power will remain same for both type of turbine, that is Pelton wheel and Francis turbine. So next efficiency is our mechanical efficiency. So what is mechanical efficiency? It is the ratio of power available at the shaft of the turbine to the power delivered to the runner. See what is happening here. Water is coming and is striking the blades, and then after striking the blades, what is happening? The blade start rotating along with runner. So runner is getting energy from water, and this mechanical efficiency is how much energy that runner is getting, which is being transmitted to the shaft. It is happening because the two energies are different because there is a loss of friction between the runner and the shaft. When the power is transmitted from runner to the shaft, there is a loss of energy due to friction or some other losses, and that comes under the category of mechanical losses, and that's why we call it as a mechanical efficiency. So what is mechanical efficiency? It is the ratio of power available at the turbine shaft to the runner power. So mathematically, we can write it shaft power by runner power. And the formula of runner power will be same as that of we have discussed in last slide. And shaft power, what is shaft power? It is the power output or the power that we are getting at the end of the turbine. Okay, so this is shaft power. So with the help of this two efficiency, that is mechanical efficiency and hydraulic efficiency, we can calculate overall efficiency. See what is happening here. Earlier at the beginning, how much power water is having? That is water power. When water is striking the turbine blades, how much power water power is converted into or transmitted into the runner is called runner power. And from that runner power, how much power is transmitted to the shaft is called shaft. So hydraulic efficiency is the ratio of runner power by water power, and mechanical efficiency is the ratio of shaft power by runner power. So overall efficiency is final output upon initial input. So that is the ratio of shaft power to the water power. That is shaft power to the water power. And if we will see this formula closely, we will see that this overall efficiency is the product of mechanical efficiency and hydraulic efficiency. So this is the important relationship between the three types of efficiency. Okay. So when we multiply hydraulic efficiency and mechanical efficiency, what we will get? We will get overall efficiency. Okay, so I hope it is understand by all. This SFSP shaft power and overall efficiency of the unit. So final output upon input. So final output is our shaft power which we are working, which because of which we are setting our plant, and whatever amount of energy available with the water is called torque. Okay, so here it is also written that there is exists a relationship between three efficiencies, that is the product of hydraulic efficiency and the product of mechanical efficiency will give overall efficiency of the turbine or water turbine, you can say. And the two formulas are same for Pelton wheel and Francis turbine. Now the last efficiency, that is volumetric efficiency. So what is volumetric efficiency? It is the ratio of volume of water actually striking the runner to the volume of water supplied to the turbine is called volumetric efficiency. See what is happening here. When water is coming from the dam and it is coming to the penstock, and from the nozzle when it is coming out, not all water is striking on the turbine blade. Some water are just go without striking the turbine. So the volumetric efficiency is the volume of water that is actually striking the turbine blade to the volume of water that is coming through the penstoke and getting out from the nozzle. So this is the ratio of actual water striking the runner or the blades to the actual supplied of water to the turbine, and that is called volumetric efficiency. So this is about the head, that is gross head and net head, and four types of efficiency, that is hydraulic efficiency, mechanical efficiency, overall efficiency, and volumetric efficiency. This all will be very useful for solving the numericals of Pelton turbine as well as Francis, Kaplan, all types of turbine. So these formulas are common for all types of turbine, and that is why it is very important. Thank you. Thank you very much.